Hola, muy buen día tengan todos ustedes. Muchas gracias por acompañarnos a un evento más de GTS Pyrometry Experts. Mi nombre es Víctor Zacarías y soy el director de GT en México. A nombre de todo el equipo de GTS Querétaro, Coahuila y Sonora, les damos la más cordial bienvenida. Nuestro presentador el día de hoy es el doctor Steve Offley y el tema para la sesión del día de hoy son los perfiles térmicos y perfiles ópticos en procesos de brazing en hornos continuos. Antes de iniciar la presentación, les queremos compartir que vamos a tener una sesión de preguntas y respuestas, por lo que les pedimos que nos hagan llegar sus dudas al final de la presentación o a través del chat o el panel de preguntas que se encuentra en la parte inferior de la aplicación de Zoom. Perfecto, pues vamos a empezar de una vez y vamos a darle la bienvenida al Dr. Steve. Voy a cambiar a inglés, si nos puede seguir. De todas maneras, cualquier pregunta nos pueden hacer durante la presentación. Hi, Steve. Welcome. Thank you for joining us today.
Thank you, Victor. I appreciate the opportunity to be with you and obviously the rest of the people on the call today with our webinar.
Excellent. We are happy to have you. So tell us a little bit about yourself, Steve.
Okay, Victor. As you've introduced, my name is Dr. Steve Offley, but those who know me well probably know me more by my nickname, which is Dr. O. The O is obviously because of my surname, but interestingly, being in the industry of heat treatment for over 25 years now, I have played or been involved in ovens and furnaces a great deal. So my nickname since the early days has been Dr. Oven. So Dr. O is what they call me, and that's who I am. And I'm pleased today to present on through process temperature monitoring of brazing processes. And as you can see from the slide, as product marketing manager at Phoenix Temperature Measurement, my desire is to introduce new technologies into the heat industry, heat treatment industry, for monitoring and measuring both product and process temperature continuously, particularly for continuous ovens and also for surveying in batch applications.
Excellent. Yeah, actually, the GTS expertise is actually in measurement. So this is just the perfect webinar to end this season. Excellent. So, Dr. O, what are we going to see today? What are the contents of this presentation?
Okay, so Victor, the presentation is split into two sections, two halves. But what I'd like to do is to introduce the concept of what I call through process temperature monitoring in a brazing environment. So what we're going to talk about is why do we need to do temperature measurement of the product as it travels through the furnace? What are the reasons for that? What are the benefits that can bring? But with a particular focus on the technical challenges of how we go about doing that, because the brazing process itself brings some very difficult challenges to the type of equipment we're using, both with the chemistry and the environment inside the furnace, potentially damaging the equipment. And also we don't want to damage the environment inside the furnace as well by doing the physical test. So that's the temperature monitoring part of the presentation. But then I'd like to, and I'm excited to discuss a new technology that is complementary to the temperature profiling called optical profiling. And this is a technology that's relatively new in the market, whereby you can actually monitor not just the temperature of the product, but you can actually see what's actually happening inside the furnace, which that complementary information along with the temperature profile information can be very, very helpful.
Of course, it is. That's really interesting. We're really excited to know about that. Excellent. So the first thing that we need to discuss is about brazing industry. When we talk about industry, what kind of parts are we talking about?
Okay, so obviously whenever we're talking about aluminium brazing, obviously the first thing that comes to mind is the manufacture, particularly in the automotive sector, of radiators, condensers, evaporators, whole host of different products whereby you have basically a aluminium substrate which has to be physically manufactured by the joining of aluminium parts using the brazing principle. So using the alloy, filler alloy to complement the aluminium and create this permanent bond between aluminium filaments, whether it be the pipes or the fins in the radiator itself.
Right. So there's one thing that we need to consider here. In the past events about brazing, we talk about other materials like copper, bronze, stainless. When we talk about aluminum, we have a particular challenge, right?
We do. Well, the first challenge is you call it aluminum, I call it aluminium. So there we go. That's our first challenge of today's presentation. But yes, the challenge you quite rightly alludes to, Victor, is the fact that obviously we're selectively melting the filler metal with the aluminium. So what we don't want to do is to take the temperature of the filler metal too close to the temperature that the aluminium substrate or the parent material could potentially melt. And that window, that temperature window, is quite tight in aluminium brazing, because typically the filler alloy is going to be melting between 580 to 620 degrees. And as we all know, aluminium will melt close to around about 650, 55 degrees Celsius. So we need to be fairly accurate as to how we control the temperature of that radiator to prevent potential damage to the substrate in the actual brazing process itself. But we also need to be able to control the temperature of the filler alloy so that it melts at the right rate, and then it flows, and then with the capillary action, it then fills the joint where you want the actual physical connection to be made, which is then reliable and will give the physical strength to the product post the brazing process itself.
Right. So we're going to talk during this webinar about the challenge of temperature, but we also need to have in mind that atmosphere is going to play really bad because this is physics. So this is going to hurt us a little bit in case, well, most brazing processes, atmosphere is something that we need to control it, to have in mind. So we need to talk about controlled atmosphere brazing, right?
We are, and that's what the majority of this presentation will be on, is the monitoring of cab processes, so controlled atmosphere brazing, where you've got an environment inside the furnace which is being controlled to overcome the one pitfall of the aluminium brazing process, which is obviously the formation of aluminium oxide. Because if you don't control the environment inside the furnace, the oxide layer forming on the substrate itself will prevent the alloy filler metal from actually flowing correctly into the joint, and you won't then get the good fixing and the good secure point of securing at that between the pipe and the fin, which could cause degradation or failure in the field.
Correct.
So obviously in the cab furnace, we're trying to remove both oxygen and water to avoid oxide formation on the part. But obviously we're also going to be using flux technology to enable us to clean the aluminium surface itself to remove any residual oxide post degreasing operations.
Right. On our first webinar of this season, we talked about vacuum brazing. And the nice thing about vacuum brazing is that because of vacuum, you remove all the contamination by mechanical means. Although the problem with vacuum is that it's limited, the production rate is limited. So most of the applications will be run, especially in automotive industry, will be run on a continuous furnace with a controlled atmosphere brazing. So that's the reason we need to talk about flux. So right now we already discussed temperature, atmosphere, flux, but there are other factors, critical factors that we need to have in mind, right?
There are, and I must admit I have to put my hand up and say I nicked this from somebody else's presentation, the 7 critical steps to brazing. But the reason I put this slide up here is the fact that along with selecting the correct alloy and cleaning the material so that there's no oxide, there are 3 items in this list that are all temperature critical. So it just emphasizes how important temperature control is in the brazing process itself. Now, furnaces come with fairly sophisticated control systems these days, but at the end of the day, you need an independent way of being able to understand what's actually happening inside the furnace. What's
Correct.
the temperature of the product? Because the furnace control system tells you what the ambient temperature inside the furnace is, but it's never going to tell you what your product is actually experiencing. And obviously, when you've got different sizes of product, you're going to get different heating rates.
Correct.
So
yeah.
After you.
Yeah, right. So one of the things that we always discuss in our presentations is that the actual temperature that you see on the controller, on the temperature controller, is the temperature of just one point located in the furnace. And that point is the tip of your thermocouple, of your control thermocouple. So that does not mean that that is the temperature or the actual temperature of the whole furnace, neither the parts. So we need to have in mind that, like you mentioned, that we need to understand what is going on inside the furnace. That's the whole purpose of of this presentation. So yeah, so let's talk about chemistry and the thermodynamics inside the furnace.
Yeah, certainly, Victor. And as you said when we were discussing earlier, we're both chemists, so this is the sort of stuff that gets us excited.
Yes.
When you have big names for words for chemicals and chemical formula, and that gets me excited. So taking
we all
those
get excited. We are a couple of nerds.
So if we take that list of 7 things that are important in brazing, we've identified that 3 of them are temperature related. So in the manufacturing process of brazing, we need to, the first major step is to perform what we call thermal degreasing. And that's obviously to take any hydrocarbons or lubricants that may be poisoning the surface of the product itself. Because if that stays in the, when the actual brazing process occurs, that's going to cause some contamination of the process itself. Probably the most important thing, though, is the use of the flux, as I alluded to before.
Right.
And this is basically the use of, for instance, in the Knockalox process, potassium fluoroaluminate, which is a chemical which enables, basically eats the oxide layer and leaves the aluminium surface clean for the brazing process to occur. So the product will obviously be either sprayed or impregnated with the flux material, which then will melt at 565 degrees. So that is critical to the surface preparation before the braze process itself. And then obviously the filler metal has to melt and flow. Now, this is where we have to have control, not only of the temperature to achieve that melting, but we also need to ensure that we've got uniformity of that temperature across both the product, or from product to product, or within the process. And in many cases, even the ramp rate, the rate of change of temperature, will also be critical as to how that metal flow occurs, and also with the flux itself, as we'll see later on in another slide.
Right. So over the past webinars, we have discussed that it's either bad to have too much, and it's either bad to have too less. Too much temperature is bad. Too less temperature is bad. Too much time it's bad. Too less time is bad. So this is kind of a process that has to be almost perfect. So that's the process we are dealing with. So can you show us how the process looks if we over the whole furnace, or the whole length?
Certainly. As everybody can see, hopefully on the slide in front of us now, this is what I would refer to as a temperature profile of a typical cab brazing process. So this is a temperature trace which is measured through the whole of the furnace. Now, when I say a profile, it's the best way of describing that is really like a thermal fingerprint, because the shape of this trace is indicative of the particular furnace or the product that's being monitored. So this shows you a lot of valuable information on a single chart. Now, you'll notice that there are multiple traces of different color, and that's because different thermocouples were attached to the product and as it was measured through the furnace. Now, a profile like this can be measured, or it has done traditionally, by a technique that we call trailing thermocouples. Very long thermocouples are fed through the furnace with the product, and an external data logger is then used to record the profile. Now, although that is useful, it can cause potential problems both from a safety standpoint. Obviously, putting a thermocouple through a furnace and hand feeding it can be very, very dangerous. Often you're restricted as to how many cables you can put through without them getting tangled or caught up in the furnace. And probably the most problematic part of it is, in order to do that sort of profile, you can only do it really by attaching to one radiator and running through an empty furnace. Obviously, this means you can't do it during a production run. And secondly, you're not really mimicking what that radiator would see in a production environment, because it's going to go through on its own. The thermal mass or the loading in the furnace will be different from that in a production environment. So that's where through process temperature monitoring comes into its own, because what we're doing is, rather than trailing a long thermocouple through the furnace itself, we're taking a data log with multiple points of measurement, multiple thermocouples, and we're sending that data logger through with the product through the whole process. Obviously, we need to protect the data logger from the environment of the furnace because of the 600 degrees for the duration of the run. So we need a thermal barrier which will protect that data logger, keep it at a temperature where the measurement is still being performed accurately. And it will also protect the data logger and the thermocouples through that process. So you can do multiple points of measurement, up to 10, or in some cases even up to 20 if you wanted to. That's a bit overkill in my view, but we're achieving the same profile. And from this profile, that thermal fingerprint will tell you how your process is working. And it's unique to that furnace, and it's unique to that product on that particular day. So it gives you a snapshot or a golden template of how your process is working.
A picture, let's say, of what your process is actually.
Yeah, and that data can be invaluable to understand possibly when things are going wrong in the process, as we'll discuss in more detail later.
Correct. Okay, so talking about specifically profiling or temperature profiling, there's a couple of challenges that we need to have in mind, right?
There is. Obviously, if we're going to send the data logger through the furnace, we need the thermal barrier, as I've explained. Now, what we don't want to do is, by the process of actually doing the monitoring task, influence or affect the actual environment inside the furnace, because as its name suggests, controlled atmosphere, we want to keep that controlled environment in the furnace. Now, traditionally, thermal barriers obviously can, the traditional design, which are made up of microporous insulation and glass cloth, they can perform an operation that we refer to as outgassing. So air or moisture inside the material can actually escape the barrier, and obviously that would then poison the environment inside the furnace. Now, the last thing you want is any air or oxygen or water getting inside a environment where you're trying to remove or prevent oxide formation on the aluminium. So we need to make sure that the barrier doesn't contaminate the process itself. At the same time, the flux material that we're using to remove oxide from the aluminium surface, that chemical, if it comes into contact with moisture, it can form hydrofluoric acid. And that is obviously a very corrosive acid, which doesn't particularly treat things like microporous insulation or glass cloth very kindly. It will eat it away. So over a period of time, you can actually damage the thermal barrier if it's not designed correctly. Now that will obviously cause physical damage, but it will also compromise the thermal performance of the barrier over a period of operation. So after months or years, it may be that your thermal barrier isn't then able to protect the data logger as efficiently as it did on day one. So these are the sort of design constraints we have to be a little bit careful of when we're designing specific solutions for this type of application.
Right. Yeah, because then regular thermal barriers that we use is usually focused on traditional heat treatment environments, let's say, where most of the cases, or where in some cases, the atmosphere is not, it's not a problem, especially when you're doing vacuum. Well, there's no atmosphere, so that's not an issue. But here we need to have in mind the design for the thermal barrier specifically for this type of brazing, right?
Correct. And as you can see on this particular slide now, there's a photograph of a traditional thermal barrier, which is what I call a clamshell design. So you've got a lid and a base. Now the base basically has the data logger sitting inside it, and there's a glass cloth and the microporous insulation underneath it. And as you can see here, this is clear evidence of where the hydrofluoric acid has attacked the internal materials inside the barrier. And it's beginning to eat away at the material, so it's going to be less efficient in its thermal protection. And obviously, the last thing you want is for that that dust or that material to escape the barrier as well into the furnace environment, because you're going to create a dust risk or a contamination risk at the brazing or the melting part of the furnace process.
Right.
So this is the traditional methodology, but obviously what we have designed to overcome those problems is the thermal barrier that you can see in front of you. You'll notice at the front of the barrier there's like a drawer which you pull out. Now in that drawer, the microporous insulation and the glass cloth is completely encased in a metal structure. So the direct contact with that and potential contamination from hydrofluoric acid is eliminated completely. So it removes the risk of deterioration of the thermal barrier. The barrier is designed so that in the manufacturing process, it's actually heated in a vacuum furnace, and it's actually flushed so that any air inside the material is removed. And you can also, if you want to, you can actually flush the system before each run to backfill with nitrogen gas. So you're actually eliminating the risk of any contaminant, oxygen or air inside the barrier escaping as it travels through the furnace.
That's a good tip. By the way, do you recommend to do that also for other types of thermal barriers?
Brazing is probably the most classic example where this is beneficial.
Okay.
The obvious downside of it is you're always fighting in thermal barrier design as to how to reduce conduction effect. Now, if you put metal around the insulation, you're creating a thermal pathway into the barrier. So we had to be a little bit careful how we created that balance between the robust nature of the barrier plus the thermal performance. So if a clamshell is, if there is no contamination or poisoning risk or any damage to the barrier, the clamshell will work in most cases.
Got it.
But the front drawer type design where you've got the encased insulation, it's ideal for this sort of brazing application. And you can, as you can see from the table, different sized construction and barrier sizes will give you a variety of different thermal performances to match the type of brazing process, the time and temperature that you need for your particular product manufacturing step.
I see. Thank you, Steve. So, okay, so we talk about the actual design or the engineering behind the thermal barrier, but going back to measurement, one thing that we need to have in mind, and it's very, very important, it's the characteristics of the thermocouples. You know, there are many varieties and construction of thermocouples, but when we are dealing with atmosphere, probably the mineral insulated thermocouple is going to be your best option, right?
It is. That's the thermocouple type we would normally recommend. The mineral, what they refer to as mineral insulated thermocouple. Typically a type K thermocouple, which will give you the accuracy we're looking for if it's a special error thermocouple, typically 1.1 degrees Celsius or 0.4%, depending on the temperature you're reading. It's interesting, thermocouples tend to get overlooked a little bit in any temperature measurement process. And
right.
my advice to anybody is don't take shortcuts when it comes to thermocouples. You often hear the phrase, a bad workman blames his tools. And often the thermocouple gets blamed for a lot, but it's generally, in my view, because the thermocouple isn't being used correctly, or it's not being cared for carefully enough.
Right,
now,
absolutely.
The mineral insulated thermocouple, as you can see on this slide, is ideal for the brazing process because the outer sheath, the mineral insulated materials, are fairly robust in the hostile brazing environment. You could use a glass fiber cable in terms of its temperature characteristics, but it isn't going to like the hydrofluoric acid potential damage in the process. So the mineral insulated has to be the go-to thermocouple for this particular application. Be careful though, because I've seen a lot of customers using these thermocouples and they look bulletproof, they look bomb-proof almost, and they think they can take them through fairly severe handling. Mm-hmm. Now, at the core of the mineral insulated thermocouple, there are two very thin wires which make up the dissimilar metals for the chromal and the lumal legs of the thermocouple. Now, the outer sheath may not look as if it's damaged, but if you stress or strain that cable repeatedly or bend it round a very tight radius, you can actually physically snap the legs of the thermocouple internally. Now, what that does is it creates what we call a new hot junction. Typically, the hot junction is at the tip of the thermocouple, but if you break it or you snap it, a new hot junction will form somewhere along the length of the cable, which is not where you want that measurement to be. So be careful of the thermocouple, and also be very careful how you place your thermocouples. Spend some time designing an experiment to know how to physically secure the thermocouple tip in the radiator itself, sandwiched between the fins where you want it to measure. Secure it off with some high temperature tape so it doesn't move even if it gets pulled. And make sure that you've got clear documentation to show others as to where you've done your test, because somebody will do the same test in the future. And every time you change that position of the thermocouple, you will get a different profile trace. So make sure you've got consistency of measurement, and make sure you know where the tip of that thermocouple is positioned.
Right. So one of the things that we always teach in our presentations about temperature measurement is that you have to be very specific when you purchase thermocouples. Because I can't tell you how many times we have received requests for a thermocouple. Well, that's incredible generic. So the thermocouple can be in different shapes, in different configurations. For this particular case, we also recommend this type of thermocouples. We do not recommend the fiberglass insulation because we normally use type K thermocouples, which are made of nickel and chromium. The problem with chromium is that it's very reactive. So every time you reuse the thermocouple, you're losing material, or you're having the chromium reacting with some other metals. So the first thing is, we prefer that you use these kind of thermocouples, the mineral insulated, which, by the way, we call it in this side of the continent, or this side of the sea, we call it MgOs, from magnesium oxide. And also another thing, the color of the connection in this side of the earth, it's yellow. So don't be worried you see a green cover. That's the same. That's actually the way it should be, because that's the ISO code. But well, anyway, we're here in the US and Mexico and Canada, we use yellow to describe K. So yeah, in any case, the thing is that we do recommend to use mineral insulated for this type of applications. We totally agree. And as you mentioned, do not treat the thermocouple like it is invincible and indestructible. Every time you are dealing with the thermocouple, you are causing damage. So please be careful. Please be careful. I cannot encourage this enough. Treat your thermocouples properly.
Yeah.
And lastly, thermocouples do not last forever. They have a finite life. Actually, both CQI9 and AMS 2750 provide a really good guideline of how many times you should use this type of thermocouples. Because every time you put the thermocouple inside the furnace, you are causing some cause of damage, of deterioration, that it will sum up every time you put it inside. So just remember, thermocouples do not last forever. They need to be replaced eventually. Here at GTS, we recommend, when economy and financial is possible, to use the thermocouples just once, preferable. That is very critical, especially if you go really high in temperature, closing to 1,000 Celsius or 2,000 Fahrenheit. Yeah, that's going to cause a lot of damage to the thermocouple. But that's, again, an economic issue we're not going to discuss right now. But we need to emphasize that you need to treat your thermocouples properly. Okay, enough of thermocouples. What is next, Steve?
Okay, Victor. So we mentioned a couple of slides back the profile and how important the shape of the profile is to understanding how the process works. From that profile, there's certain calculations or data you'll need to particularly focus on in order to fully understand whether your braze is being satisfactorily achieved or not, which we'll look at in a bit more detail on the next slide.
Excellent.
So we've talked about absolute temperature. Am I achieving the right brazing temperature, and is that, or am I achieving the right temperature to melt the alloy? But we've also got to be careful that we've got a good control of the heating rate of the process as well.
Right.
Particularly when we talk about the flux process, which is critical to the surface preparation of the aluminium. If you don't heat that at a uniform rate, if you heat it too slowly, what tends to happen is the flux material will dry out preferentially, and it will then be less effective in terms of performing that cleaning operation on the surface of the aluminium. The actual brazing temperature, the critical peak temperature of the profile itself, is obviously critical, and we're looking for uniformity. What we don't want to do is exceed that temperature too greatly, because obviously then you may end up potentially getting close to the aluminium melting temperature, and we can get what we call filler metal erosion, where the alloy metal starts to eat into the aluminium substrate surface itself. Uniformity across the product is essential, and typically we're looking for a minimum spread of less than plus or minus 5 degrees Celsius over the product itself. Now, you've got to be careful, and we'll talk about this on the next slide or two. When you think about the way that the radiator is constructed, there are going to be areas where there's bulky metal for the fixture of the radiator, which might be hindering the heating rate of the actual fins in that vicinity, and therefore maybe selectively affecting the brazing in particular areas of the product, which you need to be careful about. Temperature is obviously critical, but obviously with the profile, we're able to measure not just the temperature, but also the time at a particular temperature. And therefore, you don't want to be at the brazing temperature for too long, because again, filler metal erosion of the substrate may be a problem if you keep that temperature for too long, where the alloy metal is actually in contact with the aluminium at that elevated temperature for too long. It's going to erode the surface itself. Okay, right. So some critical areas of measurement that you need to perform.
Yeah, and thank you that you are bringing temperature uniformity. The most of the questions that we usually receive is, how much overshoot is it acceptable? And our response is always, well, none, zero. especially when you look at the temperature of your metal or your base metal, and the temperature of your filler metal, that it's so close that even just a little bit overheating is going to affect your base metal. So yeah, that's actually the reason no specification allows overshooting. Sorry, it's not going to pass. We need to look at the furnace and see what's going on and fix it. I'm sorry, I need to bring that. Yeah, we get this so many times. But you have a really good point. What can we do to optimize a little bit better our process or our profiling?
Okay, Victor. So obviously, if we're able to measure the product temperature through the furnace, when we're talking about uniformity, we're talking really in this particular case, not the uniformity of the furnace, but we can also use the same technology. We're talking about uniformity of heating at the product level.
Right.
Right. So you can, by selective placement of the thermocouples across the product itself, you can actually measure whether there's any temperature imbalance across that product. So on the drawing or the image in front of us now, you can see two positions of thermocouple placement. One's yellow and one's red. Now you can see the yellow thermocouple is closely close to a structural component of the radiator, which looks relatively bulky. So when you're thinking about putting your thermocouples on the radiator, look for areas where there may be significantly more metal or more mass, because if there's more mass, there will be that will generally create a slower heating rate. Right. So you're looking for areas of concern. Don't just simply pick uniform positions on the product, because you will then get an easy solution to your profile. Look for the challenges, because that's where you're going to end up with the product problems. Okay, so different products, obviously different size of radiators will heat at different rates. So we can use the profile to see how our range of products vary within each and every furnace. And you may want to then customize your control of the furnace to reflect the type of product you're doing. The product placement on the mesh belt may also be a challenge, because you may have slight differences in temperature from the left to the right of the belt. And if you've got products going through the belt in tandem, side by side, one product may see one set of conditions and another. So you can see what the uniformity over the mesh belt is through the process. Also, as we talked earlier, when we were talking about the trailing thermocouples, one important thing is make sure you do your thermal profile in a production matching conditions. The nice thing about using a barrier, you can actually put the test piece and the barrier and the equipment inside a production run. So leave a little bit of a gap between the leading radiator and the following radiator, but you can put it into a fully loaded furnace, and you then get a true reflection of what the production conditions are. Okay. Now, the nice thing about doing these profiles is I've often heard complaints from customers saying, why should I buy a temperature profiler? My furnace is working perfectly. Now, my standard answer to that is, if your furnace is working perfectly, this is exactly the right time to buy a temperature profiler. Because if you can create a profile of the perfect process, you've then got a golden template that you can use to monitor your process in the future. Whether that's to identify catastrophic failure, maybe a component inside the furnace has failed significantly, like in a particular zone, maybe a heater's gone down or whatever, or there may be a slow and gradual deterioration with time. Maybe a recirculating fan isn't working as efficiently and it's slowing down over a period of time. You can pick up those catastrophic failures, but also the more tricky gradual deteriorations. Now, if you can see that your performance is dropping off, you can maybe do some proactive service action without having to get to the critical point where the quality is affected and you have to stop production.
Right. Perfect. So I think we have covered so far everything related to temperature profiling. So do you want to go to do a summary about this?
Well, very quickly, Victor, yes, I think I think hopefully we've shown how important understanding what the product profile, the temperature profile of the product is in the furnace based on the brazing application itself. But obviously it's not an easy application to monitor because of the flux inside it and because you need to control the atmosphere. So you need a technology that isn't going to poison the environment so you can control the atmosphere without any hindrances, but you also want a system that isn't going to be damaged by the hydrofluoric acid potential risk inside the furnace if there's any moisture or air inside the materials. Because if you've got HF, you've got the traditional type of barrier, you're then going to end up with some corrosion problems, which will affect the long-term efficiency and reliability of the equipment.
Excellent, great. So this is basically all that we have for, in relation to temperature. But we are looking for this new technology about optical profiling. That's something new. Can you tell us a little bit about that?
Yes. For many years, we've talked about temperature profiling as a means of understanding what happens inside the furnace. But obviously, this is focused purely on the temperature inside the furnace. Obviously, the furnace operation is to achieve a set temperature on your product. But that's only part of the story. So a lot of customers said, I wish I could get inside the furnace to see exactly what happens or what my product sees.
That will be nice.
For a long time, we've been playing around with the concept of if we can get a data logger through the furnace, why can't we get some sort of video recording device through the furnace safely to see exactly what the product sees as it travels through on the mesh belt? So this is basically what optical profiling is. Instead of measuring temperature, we're actually capturing a video record of what happens inside the furnace. But the best analogy I can make, it's a bit like your dash cam on your car. Everybody drives along collecting video footage of what the car sees traveling down the road.
Right.
The optical profiling system does exactly the same thing. It's just the fact you're driving down a brazing furnace at 600 degrees Celsius, which brings its own challenges, as you can imagine.
Just a little bit.
Just a little bit, yeah. I don't advocate you try and drive your car down the furnace because it won't work.
Right. So tell us a little bit, what's the difference of the thermal barrier that we use for this kind of profiles?
Okay, so what we've done is we've adapted the thermal barrier design that we've used historically for the temperature profiling device and modified it to allow the transfer of both a high resolution 4K video camera and also illumination in the form of a torch or torches. So the thermal barrier is designed so that the torch and the camera can travel through the furnace, again, at operational temperatures, so up to 600 degrees. We're typically trying to keep the temperature internally within the barrier at around about 70 degrees or less, because that's the operational characteristics of the video camera itself. And we've been fighting with the challenge of how you get a optical pathway between the camera and the actual environment you're trying to capture, but at the same time maintain thermal performance and protection of those temperature critical bits of technology. So as you can see here, the barrier has been adapted with windows to allow the observation and the video capture in a safe environment.
I see. This is quite interesting. So what will be the benefits of having an actual visual inspection of the furnace?
Okay, so obviously because we're able to send this through the furnace at under operating conditions, you get an instant feedback from the furnace in the production flow. Obviously, normally furnace inspection requires you to stop the furnace, dismantle panels, somebody to visually go inside with torches and have a look and see what's happening. Now, that's not going to be at under production conditions, and it's certainly not going to be when you're putting product through. So the nice thing is that you're doing the monitoring instantaneously under production conditions. There's no delay to production by having to stop the furnace, cool the furnace down, dismantle the furnace to then have a look. And the other nice thing is that it's a complementary technique to what we're doing already with the temperature profiling. We can collect the temperature profile, but we can also show physically what happens to the product in that same environment, because the quality of the radiator at the end of the day is often a combination of not just the thermal characteristics, but of also how effectively was it transferred through the furnace. Did it travel through smoothly, or was there a rocky passage through the furnace because of an unstable mesh belt? Is there any possible damage to the brazing process itself through movement of the product, as we'll see in a few minutes?
Right. I think this is a very useful tool, specifically for the high production environment when we don't have enough time to actually find out, and like you mentioned, to put down the furnace, waiting for cooling, see what's going on. And you have the pressure of production manager that wants to have your furnace running all the freaking time. So this will be a really nice tool to actually do a root cause analysis like instantly, like, well, I don't know, an hour and 2 hours. Okay, this is it. This is the problem. This is what we are seeing in the temperature profiling, and this is what is causing it, right?
Yeah, I mean, everybody in a production environment has to at some point do 5 why analysis, root cause analysis,
right,
where they're trying to find what the true root cause of a particular problem is. Obviously, you start off with the symptom of we're getting radiator rejects. We identify the problem is due to poor braze. It may be because we've identified with our temperature profiling system that the temperature in zone 4 is lower than it should be. But why is the temperature lower? If you can use the optic system or the optical profiling system, you could possibly identify the physical characteristics inside that zone that identifies exactly what the problem is. And as we're always taught in these environments, from the Japanese in particular, they tell us to go to Gemba, which is the real place where the problem occurs. Right. And you can't get any closer than that than with an optical system where you're taking yourself completely to the point where the problem is existing inside the furnace.
Right. So if we go over to actual problems, what could we find with this profiling system?
Okay, so what is it that people want to see inside the furnace? It's split into the following sections, really. The first, probably the most important, one of the most important ones is what's the condition inside my furnace? Is particularly for older furnaces that have been in commission for many, many years, there may be some need for repair. Now, what you need to do is to be able to see internally what the condition of the furnace walls are. Now, you can't necessarily do that once you've dismantled a furnace, because you're actually disrupting the actual operation of the furnace in the process of taking it apart. So if you can see that live in a production environment, you can see where there are gaps or corrosion or damage to panels or misaligned ducts or whatever. Or if in the process there is some contamination from the actual process you're doing, which is a classic example of brazing, where you've got flux buildup, you can identify where that is. The second one is how effectively is my product being transferred through the furnace itself. The mesh belt is obviously designed to take the product through smoothly at a steady state or a steady speed.
Supposedly.
Supposedly, but obviously in a brazing environment where you've got stainless steel mesh belts, which can get distorted, they can get buckled, and they can get warped. That will change the characteristics inside the furnace somewhat. And if you can see that visually, you can identify when possibly you need to change that belt or do some repair work. Condition of the actual features inside the furnace may also be critical. Control thermocouples that may be damaged, maybe inlet pipes that maybe are showing signs of leakage. Potentially maybe fans or ducts or other characteristics. I'm talking about general furnaces now, not necessarily specifically brazing, but you can see the furnace furniture. What condition is it in? Does it need repairing? Does it need replacing? You can see that internally within that. And the last thing, which is probably the more probably exciting for the future, is that if there is a process where you visually see a change in the characteristics of the product itself, that can be very exciting. So in brazing, if we could see the flow process actually occurring at the product in the furnace, that is pretty exciting. And it's probably the first time it will be possible in a production environment. Other applications we're involved in, like painting, people are getting excited by the fact that they can see where drips or sags or other problems associated with that are being visually identified using this optical profiling technology.
Right. So if you take a look, if you take a dive into YouTube, you can find some videos of the actual filler metal going into liquidus, but that's in laboratory conditions.
Yes, yeah.
It will be really cool to actually see that happening in your furnace and see what's going on there and how it works. So I think this is really exciting. I agree. So I think you have really nice pictures here. For example, flux buildup. That looks horrible.
Unfortunately, that's a byproduct of the knock-a-lock process, and where you're putting in the flux to clean the surface. Now, unfortunately, at temperature, that's fine because it's in the gaseous state. But when the flux hits the back end of the muffle furnace, when you're getting into the cooling section, those chemicals will condense out of the gaseous phase into the liquid and solid phase, and they'll start to collect on the cooler areas of the furnace, and they create this sort of space-like stalactite type formation, which when I saw it for the first time, I was blown away as to how problematic that could be in practice. And the control of that is obviously a big headache for many people day in, day out in this type of industry. But you can see here classic examples of the sort of things you can see inside the furnace, whether you're looking close up or down the length of the furnace. You can see immediately. Also, these are static, but in a real life situation where you've got moving images, you can see how the belt is moving. Is it flat? Is it tilted? And we'll talk about that in the next couple of slides.
Right. So I think you have a really nice example here of what kind of problems we can solve proactively if we have this kind of equipment. The thing about flux buildup at the end of the furnace, it's something, like you mentioned, very common on these environments, right?
Sure. And unfortunately, if the flux was to build up uniformly, it would be probably fine. But it doesn't. There's going to be colder areas of the furnace that are not. So the flux will build up preferentially in one area or not. So it can actually cause at points a challenge for actually getting the product through. Now you can see the flux here on the roof of the furnace, but probably the more difficult challenge is where the flux builds up under the belt, because that then starts to affect the stability of the mesh belt itself and the level of the belt. And if you've not got a level belt, you're never going to get a smooth transition of your product through. Right. If you're trying to create this flowing characteristic of the braze alloy metal as part of the application, that's going to be affecting the quality of that whole process.
Of course.
Per se, okay.
Of course.
So the big challenge is we all know that flux builds up, but how do we manage that? And this is where the process engineers have to work in tandem with the maintenance teams, because the engineers want to keep their furnace up and running as much as they possibly can. They know there's going to be a clean down requirement, maybe on a monthly basis, but every time that step is triggered, it means you have to cool the furnace down, and it can take 24 hours out of the production schedule. Now, if you're closing your furnace down on a routine basis, whether you need to or not, that's got to be detrimental to your productivity and your production throughput. Right. Now, with the optic system, you can see when you need to do a clean down, rather than being forced because it's the end of the month. It's the last Friday of the month. Therefore, we're going to clean the furnace down, whether it's needed or not. But on the other hand, if there is a significant buildup of flux, which you don't even know is happening, if you wait another week, you may end up with catastrophic failure in your process. And I've been to certain sites where people are actually not able to get their radiators through the process because the flux is building up so much. And you've got people looking down the furnace with torches to see where the problem is. Now, the nice thing about the optic system, send it through, it will show you immediately where you've got areas of concern.
The problem is going to be. Yeah, you bring a good point about those process engineers who wants to have their furnace running 24/7 whole year. Well, that's good. I understand. But you have to remember that this is an auto-destructive process. So every time you're running brazing, you're destructing your furnace. So this is really nice because if you have a doubt about what's the condition of the furnace, if you want to run it for at least another 2 months, well, just run the optical system, find out that your furnace is still able to run parts, and go for it. Run that shit.
Yep.
Right. Okay, so I think there's another good example or another good benefit about this technology is to find out what's the condition of the belt, right? Because
and I think I've mentioned this briefly before, but
right.
The mesh belt is often a headache for many of the maintenance engineers. Is it moving? Is it smoothly running through the furnace?
Right.
It's not a cheap piece of equipment, so if you want to replace it, it's a major cash draw, a major investment. So you want to know when the right time is for either doing a repair or replacing that mesh belt. Now with the optic system, you can see throughout the whole of the furnace whether you're getting a smooth transition. And I've seen from video clips from customer sites where you're not seeing a level transfer. It's almost like the Big Dipper at the fair, the roller coaster.
Right.
Sometimes you can actually see the actual radiators tilting or lifting off the belt because there's been a dip. Now, that's classic of either the infrastructure or the structural framework underneath the belt being damaged, or the buildup of flux underneath the belt, which is hindering the actual smooth transfer of the belt through the furnace body itself. So if you can see whether or not you've got a smooth transition, it has to be helpful for controlling that brazing process, which is happening on the belt level itself.
Right. Yeah, that's a really nice point. We usually, at the end of the process, sometimes we have problems with low coverage, and we're wondering, well, why? Well, because your part went through a roller coaster. So that's it. I mean, it's a mechanical issue. It's not even about brazing or temperature or atmosphere. It's actually a mechanical issue that actually you couldn't see before.
Yep. And that's the sort of thing that every time we put the optic system through a furnace, we're learning something new about how the furnaces are working. It's incredible.
Yeah, that's really nice.
And the thing I really love is when you show somebody for the first time what's happened inside their brazing furnace, their faces light up, their eyes get large. When people start pulling colleagues in, say, "Come and look at this," you know it's got to be exciting. So
call the corporate, put everything down.
We're hoping it may get onto Netflix in the new year if we're lucky. It'll be exciting. There you go.
I like that. Okay.
Brazing TV. There you go.
Brazing TV. I like the name. Perfect. So let's summarize a little bit about this process.
Okay. So complementing the temperature profiling system we talked about at the beginning of the presentation, the optical profiling is being able to see live from inside the furnace exactly what's happening. So you can identify the condition of your furnace or your oven. You can see how your product's transferred through. Is it smooth or not? Are the features of the furnace working correctly or not? Is there any damage you can identify? Is there any damage to the structural integrity of the furnace? Or is there any contamination of the furnace, as we've talked in detail about the flux debris that builds up inside a typical aluminium cab brazing furnace? And you may be able to see the thermal process that you're performing if there's an observational characteristic to that. And obviously all of these things are done automatically as part of the production run without any need to stop the line, dismantle the furnace, or wait 24 hours to cool it down, and then a further 24 hours to heat it up again, because that's the challenges when you're heating at 600 degrees or even higher. So
Right.
hopefully this is a new emerging technology which will find more applications in the future. But from a brazing perspective, it is showing people how effective the brazing process or their furnace is operating from a mechanical standpoint.
This is really exciting. Thank you very much for sharing this new technology with us. So let's give a chance to our audience to write some questions. So Steve, I'm going to switch a little bit to Spanish just to
no
remind them. Entonces vamos a dar unos minutos para que puedan escribir sus preguntas. Nos pueden preguntar no solo sobre brazing, sino si quieren hacer preguntas específicamente sobre perfiles de temperatura o pruebas de uniformidad de temperatura, etcétera. Lo podemos platicar, ¿sale? Entonces, por favor, anoten sus preguntas sobre, en general, perfiles de temperatura y con gusto las contestamos. Puede ser en español. Voy a cambiar otra vez a inglés. So I'm back because we have some questions right now.
Okay.
Ramon Armendariz asked us, is this technology available for Mexico? Well, we both can respond that.
Yep.
Yes.
Certainly is.
Yes, it is.
Yes.
The next question is, does Phoenix has a representative in Mexico? Well, the funny thing is that we at GTS are the representatives in Mexico. So yes, the answers for both are yes. Yeah. We have Samuel Montejano is asking us, is this profiling technology applicable in automatic torch flame brazing process? That's interesting. Do you have a real video of the optical new monitor? How much time the brazing assembly may be at brazing temperature before silicon erosion occurs? That's a lot of questions. So let's go for the first question is about torch flame brazing. What can you tell us about this? Because mostly this technology is referred to furnace brazing, right?
It is, yes. Obviously, the concept of the through process means you're sending something through on a continuous transfer system. So I believe with the torch brazing, that would be more batch orientated, static. So in that case, you would be able to possibly use a handheld thermometer type device rather than something that is thermally encased or encapsulated to withstand the process conditions. So it's probably not ideal, but you could use the data logger separately and use the thermocouple input to record the temperature at or close to where the brazing is being performed.
Of course. Okay, the second question is, this is a question that actually I have, but I already know the answer. Do you have a real video of the optical profiling?
We do, and it's available on websites and on YouTube. So if people want that link, we can send it to them if they'd like to see it.
Okay, great. So we will send the link after this webinar. And the third question is a common question. How much time the brazing assembly may be at brazing temperature before silicon erosion occurs? Well, I think we need to talk about erosion in any case, right? The problems with diffusion phenomena, it's going to be always there. So the time, how much time is always a question difficult to answer. So I don't know if you want to take this, Steve.
As you quite rightly say, Victor, it will depend on the chemistry and the alloy you're using, and obviously the product itself. But what I would say is follow the recommendations of the alloy suppliers as to how long they suggest you keep it, the temperature at liquidus, how long you need to do that, and you can then use the profile trace to actually control or govern whether or not you're within that time window that they're recommending for that material.
Right. If I am going to give an answer as a metallurgist, and we all the time as a metallurgist respond, it depends.
Yes.
Yeah, it depends. So the recommendation, as Steve mentions, is refer to your filler metal manufacturer, verify what's the time, the time required, and then compare that to what you have in your profiling to verify or to define what's the best time. Okay, so we have here another question. Jesus Colunga is asking how much for the profiling equipment. What's the approximate cost of that equipment? Is that something that you can share, Steve?
Well, it will obviously depend on the specification of both the data logger, the thermal barrier performance, and also the software that is being used with it. It's probably not. I probably would rather not give a particular price because you can guarantee that whatever the system is, it's not going to be that price. So if people want further information, we can provide that to them post presentation quite easily if we know specifically what their application needs are.
Right. So Jesus, we can send you an email maybe to discuss what's your application, because again, it depends on what you have there in your furnace, the length of your furnace, temperature, and all that stuff. So we can contact you to discuss about that. We have a question from Victor Del Rio. Do you sell the equipment, or you can give the monitoring temperature service with the video capability? Oh, okay. Well, right now we do not provide the the video temperature capability, but we do sell the equipment. Probably that answered the questions.
I think that probably I think the question is, are you able to hire the equipment? And the answer is, our solution is generally to invest in a system that you can then use routinely yourself rather than just as a one-off action, because as I said before, you can create a profile today, but what you want to do is to compare that in the future. So if you've got your own system, you can do that. If you're going to rent it, it then becomes possibly less economically viable to rent on a routine basis.
Right. So we have another question. This question we get a lot. It says, for brazing the product, the temperature of the material, extreme conditions like summer and winter, does it affect the brazing process? Oh, we have covered this topic so many times. Unfortunately, yes, and it does not affect, like, it's not that the furnace is not isolated. The problem is that in summer, we usually have all the windows open, and then we have more air coming to the furnace. So usually that's when we have problems. Same in winter. In winter, we close all the doors, all the windows, and now we have a different environment in the plant, and now we change again the conditions inside the furnace. So yeah, it's not about the actual temperature in the ambient. It's about what do we do in the plant that actually change the settings of the furnace. You probably have seen a lot of this, Steve.
Yes. I don't think I've seen an example in brazing, but in other heat treatment applications, you've obviously got to also consider what's the starting point of your product temperature.
Right.
Now, if you've got products that have been sort of stacked up in a warehouse or a factory environment in winter for any length of time, their ambient temperature will be of a set temperature in line with the conditions inside the storage facility. And therefore, you may have a product temperature swing of maybe 5 to 10 degrees between winter and summer. Now, you've got to take that into account, that you're putting a lot of metal possibly inside your furnace at a cooler temperature than you would do in the summer. And that will have a knock-on effect on how efficient the furnace is working, because the furnace has to heat that product up through a further 5 or 10 degrees to get to the optimal temperature you need for your particular heat treatment.
Correct.
So understanding what your product conditions are pre-processing is also critical to the overall result of the profile itself.
Right. We have another question. We get this question a lot. Victor Del Rio asked, if I have a new equipment working and the mesh belt have some kind of elongation, we have already cut the length of the mesh belt 3 times. Is it normal to have mechanical elongation on the mesh belt? I don't know if that is normal, but probably having an optical system will tell us what the problem is. What do you think, Steve?
Yes, I mean, the optical system will obviously show you where the problem occurs specifically inside your process at the point where the process is occurring.
Right.
Now, that may be linked to the cause of that particular problem. It may be that there is a buildup of materials underneath the belt, or you may go to that point of the furnace and find that the structural support underneath the belt is damaged, which means that the belt is dropping or whatever. But it gives you at least an exact pinpoints as to where the problem exists inside the furnace. And if you know where that is, you can go straight to that area of concern and have a look at it visually after dismantling the furnace if you're going to do some repair or replacement action.
Great, thank you, Steve. So we almost are out of time. So we have time for one more last question. We will respond every question, maybe not live, but we will respond you via email. Don't worry about that. So hello, Dr. O and Victor. Thank you for your very interesting presentation. I believe that this equipment will definitely help to understand what's happening inside our continuous furnace. It looks like you are using a thermal barrier to protect a temperature data logger and a camera. Is it possible to use the same thermal barrier? That's kind of the question I have, actually.
Okay. Well, you will remember in the earlier part of the presentation when we were talking about the design of the temperature profiling barrier with the front-loaded drawer. And you can see the same mechanism is used for the optical system as well. So you can have the same thermal barrier casework, and you then can interchange both an optical drawer with a temperature profiling drawer. So you can use the same main construction of the thermal barrier and make it either an optical or a temperature profiling system. So you could do sequential runs, one an optical and then one a temperature run through the same furnace.
Excellent. Okay, so I think we're almost done for today. We exceeded a little bit of time, but we wanted to answer all the questions. This new technology actually brings a lot of them. So just in case you didn't have opportunity to attend to our previous webinars, remember that you can visit us at our YouTube channel. Find us as GTS Mexico. You can find all of our videos, and maybe you can find the answers about these questions about the problems with the belt, problems with temperature, problems with the atmosphere. We have discussed this all over this season, and we are really happy. We are really thankful, Steve, for finishing this season with you. It was quite it was a pleasure to have you here.
Well, thank you, Victor. It's been a great pleasure to be with you and everybody attending the webinar. So thank you for your time. I'm sorry I couldn't see you face to face, but for all those out there, thank you for your patience and perseverance. And hopefully what we've been discussing has been useful. So if you have any further questions, get in touch.
Thank you very much, Steve. Have a nice one. So I'm going to switch to Spanish. Pues muchas gracias. Como les comentaba, con este evento finalizamos nuestra segunda temporada. Estamos muy contentos de haber compartido con ustedes alrededor de estos 4 webinars pasados algunos tips sobre soldadura y brazing. No queremos finalizar sin agradecer nuevamente por su confianza en GTS Pyrometry Experts. Los invitamos a seguir atentos a nuestras redes sociales para nuestra tercera temporada que va a iniciar en enero del 2021. Pueden suscribirse a nuestro canal de YouTube para estar enterados. Les pedimos por último que se mantengan en línea al finalizar esta presentación para contestar una muy breve encuesta sobre su experiencia de este evento. A nombre de todo el equipo de GTS Querétaro, Coahuila y Sonora, les agradecemos su confianza y les deseamos un excelente día. Muchas gracias y hasta la próxima.